Hello, this is Insu.
Dan?
And Andrew, and our group is working on modeling the Bioink extrusion and retraction process for a 3D bioprinter. So why do we care about this? 3D bioprinting can potentially provide patient-specific blood vessels to replace clogged arteries. This is a typical cause of heart disease, which is actually a cause of 1 in 4 deaths in America. In 3D bioprinting, a Bioink is extruded from a syringe. The reason this process is interesting is because Bioink is actually a compressible fluid, so when you're trying to extrude the Bioink, there's a delay between a syringe pushing the fluid out and the fluid actually being extruded. Additionally, after the syringe ceases moving, Bioink will continue to drip out and excess Bioink is used. The extrusion process can actually be reversed to increase the accuracy of the 3D bioprinting so that you're retracting the Bioink and no excess Bioink is used. And our group works on modeling this Bioink retraction process. So some previous work that has been done in this area is mostly on modeling the properties of the Bioink, because this is how you're going to figure out what your retraction settings are. Properties vary with oxidation percentage, concentration, and temperature, and usually density and viscosity have been modeled, but our group is looking at compressibility, which is another key physical parameter but has not been modeled in the past. So here we have the 3D bioprinter available to us, and we're just going to zoom in on this point right here. And so we see the syringe filled with Bioink and a gear that will push the syringe down, and we hope to also modify it so that it can pull the syringe up and retract the Bioink so it doesn't drip. The controlled variable in this process is the extrusion rate, the manipulated variable is the retraction setting, the actuator is a motor adjusting the syringe height, and the disturbances in this system are air bubbles.
To model the behavior of the Bioink inside of the needle, we used engineering Bernoulli's equation. Because of the viscosity and compressibility of the Bioink, we introduced new terms such as viscous force and friction force. And we also introduced a new variable, R, which is the volume ratio of the compressed volume over the released volume. We made a couple of assumptions as well, and I would like to highlight a couple. We assumed compression due to air in Bioink, and air is modeled by ideal gas, and we also assumed that viscosity is constant throughout the retraction because retraction velocity is constant. From there, we could calculate the retraction velocity from the volume retracted. And if you look at the plot, we can see that the R value reaches close to 1 at around 0.2 seconds, and it plateaus, which is logical because of the pressure differential after the retraction.
So we're left with this equation that we see up top. You'll notice that we've whacked out the gravitational term from the Bernoulli equation. That's because the syringe is sealed from the environment. And we can measure rho trivially, so it's density. We can also get velocity u by calculating the mass flow rate and relating u to mass flow rate by density and by cross-sectional area of the needle. We measure R, and then we solve for mu, or viscosity term, because that's the last variable that we have. With that modeled, we know the retraction setting, the amount that we need to pull up. Okay, so what does this look like? We want to print this, where this circle is the Petri dish circumference, and we want to print these 4 horizontal lines after a priming vertical line step. This is what it looks like when we don't have any retraction. So you'll notice at first that the base of the Petri dish is kind of blurry. That's because there's some soap on it. The Petri dish is hydrophobic, and so the aqueous Bioink tends to bubble up, and it doesn't make nice lines like we're seeing here. So we put the soap on. Okay, this priming step is just making sure that when we print the 4 horizontal lines, we're modeling the middle of a print. And I'm just going to fast forward a little bit. So here's our last pass, and we're going to go to the horizontal lines. Now, it shouldn't be printing between the horizontal lines, but like we're about to see, we're going to drag a straight line of fluid due to the compressibility of the Bioink. You'll also notice that at the beginning of each line, we print a little bit too much, and that's exacerbated by the fluid combining with the primed line. But we don't tackle that problem in this. We just deal with the retraction setting. So this is when the retraction setting from our model is applied. So here's the end of the priming step. We're going to suck up right here. Okay, there's a clean pass, and suck up right here. So no drips there. You'll also notice that there's a pause right there. And that's 0.2 seconds, like Insu was talking about, after the retraction is all the way set. So we use our time and the amount of retraction calculated by our model. Okay, let's see what happens when we print with 60% of the retraction rating of our model. Okay, we're going to see some diagonal drips right there, right along there. And so that indicates that the actual retraction setting that our model predicted is enough, but it's not excessive. In conclusion, what can we work on in the future? We should improve the code's usability so that other bioprinting teams can apply the parameters from their Bioink to find the retraction setting. We should also adjust the initial extrusion setting so that the lines print more nicely, and add a sensor to measure the height of the fluid in the syringe, and that would just let us apply the retraction setting regardless of how much Bioink is in the syringe, because the retraction setting is going to be directly proportional to the amount of Bioink in the syringe.